There remains a gap in understanding the impact of gesture-based interactions between students and simulations on their interpretation of visualized scientific phenomena. Addressing this, our paper presents a user study conducted on a dynamic equilibrium visualization simulation developed for introductory college courses.
Our investigation context is resting membrane potential. The term resting refers to a state of dynamic equilibrium where two opposing processes occur at equal rates but in opposite directions. The membrane potential represents an electrical driving force that prevents ions from diffusing until they reach equal concentrations. The problem space involves prompting students to recognize two types of influences: a random process that is salient to students and a subtle force that is not salient to students.
Here's a video of me interacting with the simulation. After setting up the simulation, which spawns in the correct amount of ions I designated, I start the simulation. Notice the leap motion controller in front of me tracking my hand's position. As I move my hand, a ghost hand is rendered accordingly, and the randomly designated potassium ion is localized based on my hand position. We render the graph above my head so it is unobstructed by my hand. Notice the purple line representing the equilibrium potential and the black line representing the cell membrane potential are separated. Now I open the channel. Immediately, potassium ions begin to flow and the two lines converge. The cell is in equilibrium. Notice that the potassium and chloride ions begin to align across the membrane. This is to emphasize the electrical driving force. Also notice that I'm unable to always move the potassium ions across the channel, even when it is open. Again, the electrical driving force is preventing me from freely moving my particle across. The most important feature of the simulation is allowing the learner to embody a designated potassium ion with their hand, which is accomplished with the leap motion controller. To increase the visual saliency of the designated potassium ion, it is shaded with a lighter hue of purple, and the positive symbol is colored white as opposed to black. The XYZ position of the palm is transmitted to the simulation and is used to localize the designated potassium ion. The corners of the gesture plane correspond to the corners of the monitor, allowing the potassium ion to reach all parts of the simulation without gesturing across large distances.
In our study, 40 undergraduate students who were not majoring in biochemistry participated. This photo illustrates the setup of our research. Interestingly, despite having no previous experience with gesture-controlled simulations, all students found the system easy to control. More importantly, the majority expressed a deep connection with the learning material while using the simulation. For more details, please find our paper.
In summary, participants in our study were comfortable with the gesture controls, and using gestures seemed to make the experience more immersive, and they were conducive to helping the participants understand the core ideas. However, in order to make some of the more nuanced aspects of the simulation more salient, our next step will be to create a custom haptic glove that can accompany the gesture controls and indicate those more subtle effects.